Some people might think I've got a phobia about Houston, and there might be even a little of that, but actually I love LPI and I love the Johnson Space Center, and it's really good to be back here. I feel very honored here, and I'm even going to reflect for a minute or so on what Houston has meant to me. First, a lot of my friends I see here and just about nowhere else. I mean, friends from ASU, Brown, JPL, NASA Ames, all over the world, from Europe, from the floor below me, in my old building. It's a wonderful place. The science is always wonderful. And Houston came into my consciousness going all the way back to the Apollo program for obvious reasons for someone my age. And my first science conferences that I ever attended was at LPI, the old LPI building, the old house is where we met for our Wednesday night chili cook-off, and the Johnson Space Center at Gilruth Center for the conference. So Houston is deeply rooted with me, and so phobia aside, I really like being here, and especially for this conference. My first two science presentations ever, in 1983 and 84, were about Enceladus. The first time I gave a poster on basically plate tectonic-like deformations on Enceladus, and the second time I talked about a crater pit chain, which wasn't just a crack and there are holes in the ground, so it must be cryovolcanism. So basically that's what I said, and and I even talked about cryoclastic volcanism before that word came into existence. So I want to say move over, Candy Hansen. I have been doing some image processing myself, and if you look carefully, absolutely stunning. But really, seriously, this is as real as it gets. I mean, you can call them geysers, call them whatever the hell you want, but I'm calling them cryovolcanoes. So what about the word cryovolcanism? The word. Planetary volcanism, that's where it's rooted in, of course, our familiar concept of planetary volcanism. Anybody who's been watching TV lately, in between Donald Trump, has been seeing a lot of planetary volcanism from here on Earth. So it's an eruption from an opening on a planetary surface from which magma, defined for that body as a partial melt product of mantle or crustal material, is erupted. That's Rosalie Lopez's definition, and that's what I'll stick with. So the etymology of the word, it comes from a French word which derives from the earlier Latin Vulcan, who was the god of fire and metalworking. Okay, we kind of knew that. The etymology of cryovolcanism is from the word volcanism and the Greek kryos or cryos, meaning icy cold. Hence, it's icy cold volcanism or cryogenic volcanism. The word cryovolcanism was coined by Steve Croft about 1988 or so, when we just were kind of in chat mode looking at Voyager images. I adapted it in my dissertation on cryomagmatism in the outer solar system. And it's cryovolcanism is the root word, the basis for terms such as cryovolcanic, cryomagmatism, cryoigneous, etc. So cryo-lavas are erupted melt products due to partial melting of icy bodies, crusts, or mantles. They may consist of aqueous liquids or suspensions of solid grains and gas bubbles in aqueous liquids, or they can be nonpolar liquids containing suspended gases and solids. So a few examples. So this is the real side, and I think these are all actually probably excellent candidates for cryovolcanism. The only one that we're damn sure about, in the 99.99% sense of the term certainty, is Enceladus, where we see stuff ripping and tearing, jetting, shooting out of Enceladus. But the others, I think, are also pretty compelling cases. Triton is where I got really excited in 1989 with the landscapes there. You know, are they cryovolcanic? I don't know for sure, but they sure look cryovolcanic to me. These crater chains look like rift-aligned pits with smooth deposits, and you know, it looks pretty compelling to me. This is one of the coolest cases. This is from some of Paul Schenk's work. He gave me this slide long ago. This is the lake on Europa. It's just a couple kilometers across. It's not very big, but it's pretty awesome. This smooth deposit here, and he showed that yeah, the topography at this small scale isn't the greatest, but he pretty much showed that that smooth deposit that sure looks like it's embaying underlying topography actually sits in the low ground, and I think it's cryovolcanic. However, the first principle of cryovolcanic studies is what I'll call the Cayley caution. And many of you probably already know where I'm going with this. And it is, this was one of my favorite books back in April 1972, which was the year and the month of the Apollo 16 landing, and the month I turned 14 years old. This was the more important event of those two. So this book was a preparatory book, just kind of getting everyone all excited about why the hell are we landing there, specifically there. It's because of these smooth deposits that seem to lie in the low ground and embay this more rugged upland. And there's a lot of this stuff. It's spread widely over the lunar surface. And it was pretty much assumed that this was some kind of ancient volcanic deposit, younger than the more rugged, little bit higher uplands. And so the reason we went there was so that we could look at, I was 14 years old, but I'm using the term we in a pretty broad sense. Humanity could look at these plains as well as the rugged uplands. So you can see the traverse there. So they even had an ultraviolet camera that could look at the horizon and look for venting volcanic gases. Okay, well, then it was found that all the rocks were breccias. There weren't any. There were volcanic rocks within the breccias, but there were no volcanic flows that weren't pulverized and ground up and sutured together in form of breccias. That the Cayley plains are a big ejecta deposit, or multiple ejecta deposits. And this is just from the LPI website. Virtually every rock collected on Apollo 16 was a breccia. So in hindsight, one of the planners said, oops. And my sum up is breccia everywhere, not a drop of water to drink nor a single lava. Now we think, and I'm sorry to Samuel Taylor Coleridge, who did the original, The Rime of the Ancient Mariner. I've really abused his poem, but that's basically the sum up of Apollo 16. So, cryovolcanism in concept, with that caution duly noted. So, the idea stems, you can trace it back to this paper and a couple others around that time, from John Lewis's 1972 paper in Icarus on low temperature solar nebula condensation, where other people had talked about the nebula condensation of rock forming minerals, in an idealized, progressively cooling solar nebula. John Lewis took that further and said, in an idealized cooling solar nebula of solar composition, a bunch of volatiles would condense out, the water ice being among them, and then ammonia, and it would form ammonia hydrate. And he recognized that ammonia hydrate, under certain conditions, is going to melt at much lower temperatures than pure ice would. So he started thinking along those lines. So early cryovolcanic concepts. So this is pre-Voyager, or Voyager as I like to call it. So John Lewis did his 1972 paper, and right before that, he published an interesting paper, which was an earlier follow-on to his other paper. I mean, the years logically would have been reversed in publication, because this is really a follow-on in a conceptual way to his 1972 paper. He talked about satellites of the outer planets, their physical and chemical nature. Some quotes: the Galilean satellites of Jupiter and the larger satellites of Saturn, Uranus, and Neptune very likely have extensively melted interiors and have an extensive mantle of ammonia-rich liquid water and relatively thin crusts of ices and a core of hydrosilicates. Well, that was prescient. Okay, another pre-Voyager study. His student, Guy Consolmagno, my academic brother, older brother. John Lewis was our mutual advisor, just different generations of students. In 1978, published on the evolution of icy satellite interiors and lavas, said he included convection, solid state convection, which John Lewis had not. Bodies of radius less than 500 kilometers will never melt. Well, okay, but he didn't include tidal heating. Those smaller than 750 kilometers in radius will be totally refrozen by present. Surface water flows are not expected for bodies of less than 1,500 kilometers radius, and even small 100-kilometer bodies may be unstable against solid-state convection, which was the big process removing heat so that cryovolcanism and oceans couldn't happen in a lot of these objects, according to these really simple pre-Voyager concepts. And their surfaces may show signs of tectonism. Well, that was dead on accurate. Post-Voyager, Dave Stevenson, on volcanism and igneous processes in small icy satellites. The most likely cause of endogenic processes is the igneous activity associated with low melting point ammonia water magma, and he credited John Lewis with that idea. Radiogenic heating probably suffices to provide the necessary melting of Tethys, Dione, Rhea, and Iapetus. Tidal heating is needed for Enceladus. Okay, that's pretty right on the money there. Migration of large fluid-filled cracks is likely, leading to surface flooding. And if clathrates are present, then pyroclasts forming explosive events can occur. Well, that's pretty cool stuff for that early on, immediate post-Voyager 1 and 2 at Jupiter and Saturn. So now I'll talk a little bit about cryo-lavas, density, composition, and rheology. So this was my first paper on the topic was on the, Steve Croft was the lead author, was on the density of ammonia water liquids. And the dashed line here, you can see this is in temperature versus density space. The dashed line is the density of water ice, and then these contours are for different compositions of ammonia water liquid. And if you take the eutectic composition of ammonia water at the eutectic temperature, well, it's just slightly denser than water ice. So at least we're within a short range, we're closing the gap between the density of water ice and liquid water. Pure liquid water is going to have a hard time to erupt over pure water ice due to the density difference. And so ammonia helps a lot. Maybe not quite enough, suggesting still that exhaled gases are important. Throughout the 1970s and 80s and 90s, there was a lot of effort given by spectroscopists using telescopes to try to detect ammonia in the outer solar system, and a whole lot of failure to detect it. They found a lot of other stuff, especially water ice, but other materials, methane and other substances. But scant little ammonia, rather, very, very little, and the detections that were made were really, really iffy. But then in the 2000s, ammonia has been detected on a lot of objects now. Pretty good detections, but small amounts relative to spectrally more dominant materials. So there's also a lot of attention to the ammonia water system. Going back to John Lewis's work, I was his student. It was kind of a natural to follow in his footsteps, and that's what I did for a lot of my early career. I was looking at the properties of ammonia water X, where X is some third or fourth component, their physical properties. This is just the phase diagram of the ammonia water system. Throw in methanol, and you get a different phase relation where the minimum melting point is here instead of over here if absent absent methanol. So here's the phase diagram under various pressures. And my talk is on cryovolcanism at the surface. But of course, when we're talking about partial melting in the satellite interiors, you have to consider the pressure effect if it's a sizable body. And so Dave Hogenboom and I did a lot of work on the high pressure, not extremely high, but a few hundred megapascals pressure on the ammonia water system. And I drew an analogy to the forsterite silica system with enstatite in the middle there, where as there's a paratectic relationship, and I'm not going to go into the details of some of this terminology, but there's a paratectic relationship at low pressure, and as you apply high pressure, it shifts over a thermal divide to the ammonia, the water-rich side of that divide. And it's very analogous to what happens in the forsterite silica system, which has a big implication for the nature of volcanic rocks on Earth. Alkaline volcanic rocks versus non-alkaline, or silica saturated versus unsaturated. And I mentioned already methanol, and I'm going to move on because of time. I also looked at the rheology of the liquids and of liquids containing suspended ice solids. And this is for the ammonia water system, the binary system. And these curves are curves of constant viscosity versus in percent ammonia versus temperature space, and the eutectic and paratectic are down here. And this is what the stuff looks like, and sorry, I couldn't find the original photo, so this gives it sort of a vintage look, which is what the science is. So yeah, this is from 1865, this photo. In between shooting the Civil War, this is what I was doing. So here it is, the liquid is pouring out. It's sort of syrupy or molasses-like. Here it is when this is my hand. You can barely see, and this is a thermistor probe, platinum thermocouple probe, and here's a big glop of ammonia water liquid. This contains a lot of suspended solids, and so it's really viscous stuff. And in terms of how it becomes more viscous as you add more solids, it behaves a lot like basalt. In fact, the pure liquid is about roughly the same viscosity as basalt, and then as you add crystals, it's similar in its behavior to basalt. So as you add crystals to basalt, it gets gooier, gets thicker, and same with ammonia water. And I mentioned methanol. Here we see it's a logarithmic scale, viscosity in poises, a CGS unit of viscosity, versus log of temperature. And here's ammonia water with roughly the viscosity of basalt. And here's ammonia water methanol liquid with roughly the viscosity of andesite or dacite. And here's what I presented in terms of, I defined something called the mobility index. This is a gravity scaled effective viscosity. So this is just simply the logarithm of the material density times G, I think that's a G, yeah, divided by the viscosity. And so the more viscous behaving stuff is toward the bottom of the graph, and the runnier stuff is toward the top. And here's ammonia water right along near basalt. And you can see that, for example, and the vertical dashed lines are the gravities of different objects. And so Enceladus here, the viscosity of ammonia water would cause it to behave on that low G object roughly as andesite or dacite would behave on Earth. However, I mentioned that for a long time there were no compelling detections or not very good detections of ammonia. There's not very much ammonia, at least in the inner solar system. The terrestrial planets have CO2 and N2 at Venus, Earth, and Mars. Here I'm considering carbonates as a reservoir of CO2 on the Earth. And ammonia is a biogenic trace substance on the Earth. Well, in the outer solar system, it's not that much different. There's a lot of N2 out there. There's a lot of methane out there, carbon monoxide. There's a lot of carbon dioxide. There's widespread ammonia. We now know that. Not everywhere, but many objects have ammonia. But it's only a trace or a minor amount. Comet Hale-Bopp as an example. I won't go over this long list, which is only a partial list of the most abundant materials, but Comet Hale-Bopp, according to what's in the coma, has, water is the most abundant, followed by carbon monoxide, followed by carbon dioxide, methanol, hydrogen sulfide. It's not till you get down here at 0.7% relative to water that you see ammonia cropping up. You've got formaldehyde more abundant, hydrogen sulfide, CO2. Those all are very chemically reactive with respect to ammonia. Ammonia will react with CO2 to form ammonium carbonate hydrate. It'll react with formaldehyde to form hexamethylene tetramine, and that also becomes a hydrated material. It reacts with magnesium sulfate to form ammonium sulfate, etc. And I'm going to move on quickly. Here we see the phase equilibria with, here's the binary water ammonia system. Here's the field for ammonia dihydrate. And if you add hexamethylene tetramine, you get phase relations like this. So this hexamethylene tetramine dissolves in ammonia water, and you'll still have ammonia water liquid if stoichiometrically you have enough ammonia to begin with. But if you have enough formaldehyde to begin with, then it'll eat up basically all the ammonia. And similarly with the ternary water, ammonia, carbon dioxide system, carbon dioxide also eats up ammonia. And where does Hale-Bopp sit? Totally outside the ammonia water field. So Hale-Bopp contains ammonia, but if you cook it up and equilibrate it, it's not going to have free ammonia water liquid in it. It'll have ammonium salt aqueous solutions, but not free ammonia water liquid. And free ammonia water, this is what I prepared before I even knew about, before anyone knew about Hale-Bopp. This is the quaternary system, not showing phase equilibria, but showing just the compositions of solid phases in this quaternary system: water, ammonia, formaldehyde, and CO2 at the back. And you get free ammonia only stoichiometrically if you're within this pyramid here. It's resting on top of this, this triangle. There's only a limited stoichiometric range where you can have free ammonia liquids forming. You can get ammonium, which you could say, well, that's ammonia, but in terms of the physical chemistry and the rheology, for example, and phase equilibria, it's totally different. And there's plenty more that kills off ammonia. Magnesium sulfate does, it forms ammonium sulfate. And forsterite kills it off, and iron sulfide reacts to form ammonium sulfate. So Titan the comet, I did this little mental exercise. Let's just imagine Titan as sort of like Hale-Bopp. It's not in its origin, but we can pretend. I mean, that's what most of us are doing here at this conference. We're pretending, honestly. Well, I mean, I'm being brutally honest. Unless you're studying Enceladus, in which case you're being very real. Okay, so imagine Titan as a giant comet-like body, and it differentiates and refreezes. The high-pressure mantle contains clathrates, and then you've got a gas-saturated ocean. Okay, so if it started out stoichiometrically, like Hale-Bopp the comet, and I'm not saying that it really, I mean, dynamically, it obviously is totally not a comet. I don't want to give that misimpression. But there are valid reasons that I won't go into, that maybe it's like a comet in a certain way. And if you chemically react it away, then you end up with, and it differentiates, you can end up with a crust more than 50 kilometers thick made of ice, methanol, monohydrate, and ammonium salts. No free ammonia. Now that's just a model. So thermal conductivity, I just want to make a very important point to modelers. There's a whole bunch of stuff on this diagram. This is the log of thermal conductivity versus log of temperature. Here's a thermal conductivity curve of water ice. Well, all this stuff down here are different volatiles, and notice that they all sit way below the thermal conductivity of water ice, and note the log scale. Same with various salt hydrates. Not unhydrated salts, but hydrated salts. And same with organic materials. So conclusions. There's a lot going for the idea of ammonia-water cryovolcanism in pretend world, in model world, in nebula thermodynamics and density relations, but ammonia is not as abundant as once supposed. Chemistry eats it up. Ammonia-water oceans are possible only where comet-like or interstellar or photolytic volatiles are not abundant, and Lewis ices, following that low-temperature nebula condensation paper of John Lewis, only where Lewis ices are very abundant. Is that anywhere in the solar system? I'm not sure. Where ammonia is killed off, ammonium salts are likely to be plentiful. Methanol hydrate may dominate low-temperature liquids derived from comet-like mixtures. Exsolved gases are likely needed for eruptions to occur, but there are lots of gases available in the solar system. For icy satellite thermal modelers, water ice 1H is by far the most thermally conductive, and we're talking about factors of several or an order of magnitude or more thermally conductive than most of the other volatiles that you can think of. And that's it. Thank you.
Hi there, Mark Hesse, UT Austin. So for somebody coming at the subject from the outside, what put the focus on ammonia in the first place? It seems a lot of work has been done on this, and if I understood your talk correctly, it seems like it may not be as abundant as once thought. What put the focus on ammonia initially?
Oh, yeah, that's a good question, and sometimes I might forget to point that out, but there was an intense focus on ammonia, and it stems straight from John Lewis's paper, and the idea, his paper on low temperature nebula condensation, where he was saying, hey, ammonia should condense. If you take the sun and cool it down, solar composition, cool it down enough that ice forms, and then cool it some more, then ammonia forms, if it's in thermodynamic equilibrium, and you make a lot of it, like 15% of the total volatile is ammonia. There's a lot of it. And the ammonia water melts at about 176 Kelvin. So you melt at a temperature almost 100 Kelvin colder than water ice. So if you're on a low energy budget, as the icy satellites mostly are, then it's a lot easier to melt ammonia water than it is to melt water ice. And so that is the source of that focus. And it was indeed an intense focus, and it was an acute embarrassment to those of us doing ammonia water studies, investing a lot of effort in that. And the spectroscopists were saying, no ammonia here, no ammonia there, no ammonia there. Hey, here's a little, here's one little wavelength where there's, like a 1% little dip in reflectance, and that could be ammonia. And but eventually the ammonia was popping up all over the place, but in small amounts.
So do we see ammonium salts? That's what you're suggesting
so
they should do.
Here I am saying, well, there's a lot of chemistry that makes a lot of ammonium salts, so there should be a lot of ammonium salts. So, God, now it's getting even worse. It's like, I don't know. There is a lot of attention given to magnesium sulfate, which I pointed out it should be there, and then other people said, no, like Bill McKinnon was saying, no, you've got the wrong chemistry, Kargel. You won't get very much magnesium sulfate. If you do it right, you get something else. And Tom McCord, though, came like, Europa, lots of magnesium sulfate, and then McCord saying, no, it's sulfuric acid, sulfate. But sulfates are probably out there. It seems that the near-infrared spectra do show sulfates, whether it's magnesium sulfate or ammonium sulfate or hydrogen sulfate. I don't really know. And then you get Brad Dalton with his, real sensitive spectrometer in the lab, and he says, well, these little dips here and there in the shape of the sulfate hydrate absorption band looks a lot more like magnesium sulfate and sodium sulfate than it does something else. And, it goes around and around. So I'll say that sulfate hydrates do seem to be abundant on Europa.
Yeah, this only seems to apply to the Jupiter system, though. We don't see a lot of sulfates beyond there.
Yeah. And of course, John Lewis was talking about ammonia, and Fegley and Prin and Fegley talked about ammonia being abundant in the satellites of Jupiter and Saturn, but due to the the planetary nebulae conditions and kinetic inhibition, they said, well, Uranus and Neptune, there probably won't be much ammonia, and it goes around and around.
So Jeff, I could make comments to Carl's comment, et cetera, but in the interest of time, I will just channel my inner Jonathan Lunine and remind you that Titan needs ammonia to make its nitrogen atmosphere because it didn't come in as a class.
Yeah, you and Jonathan Lunine have pressed that point, and that's a good point.
But the other thing I wanted to, and I'm sure this will come up again and again. It's just like a major, it's part of the whole reason we're here. What's going on with ammonia. But the other thing I'll tell you is like the best analysis of the Enceladus plume, by the INMS team, we see CO2 and ammonia in sub-percent, mole percent abundances, but they're both there. They're not consumed by one or another. So there's something missing in this chemical story you're telling.
I'm
not sure what it is.
I'm glad you pointed both these things out, about Titan and ammonia being the precursor of the nitrogen atmosphere, and that Enceladus is spitting both CO2 and ammonia out, and Jeff Kargel just said that they eat each other up. And they do eat each other up, but somehow it can't go to completion. Now, formaldehyde, that reaction is vigorous. and it proceeds even at fairly low temperatures. Ammonia water, eutectic temperatures, I don't know, and maybe one of you have done this reaction. If not, one of you should do this. I'm not going to be doing it. Look at the kinetics of the formaldehyde ammonia water reaction, but I would say also the CO2 ammonia water reaction, and maybe someone's done that. Maybe the answer is there and I just haven't paid attention to it. But I agree.
Yeah, okay, well, the Enceladus Ocean is almost certainly near 270, not it.
Yeah, so either somehow they're sitting in different pockets and they end up getting mixed. That sounds pretty contrived. Or somehow the reaction just does not go at the temperatures prevailing inside Enceladus.
We can.
So there's been detection of ammonium all over Ceres in the silicates, and we have evidence for ammonium chlorides in some bright spots on Ceres. So actually, I like your story. I mean, for Ceres, it's true that the ammonia got turned into.
Okay, I'm sorry. With my bad ears, I'm not sure.
And my French accent. I said there is ammonium all over Ceres, the dwarf planet. And there is ammonium chloride in some places on Ceres.
Ammonium chloride?
Yeah.
In what?
In Ceres.
Oh, in Ceres. Oh, okay. Okay,
Sorry.
yeah. Okay, yes. I haven't mentioned anything about Ceres, and that's a good point. You know, that my talk would have been totally incomplete, a lot of loose ends if it wasn't for the comments and questions. So I thank you very much.
And so my question was about chlorides. There are, I did not see them in your slides, but you had them mentioned in your 1991 paper about brine volcanism.
About chlorides?
Yeah.
And chlorides and Enceladus as well. Yeah. Sodium chloride, not much, but there's some. And so chlorides are also obviously, I think, an important. So we see a lot of chlorides in the Earth's ocean. We see chlorides on Mars after a long time searching. Then chlorides were finally found on Mars, and they seem to be very abundant. And chlorine is cosmochemically abundant, and you know, unless the conditions are such that chlorine goes into a metal phase, like they do in some extremely reduced objects, then chlorine is free to be a volatile. And if there's water kicking around, it will generally form sodium chloride. And if you had a lot of ammonia as well, it would form ammonium chloride. Yeah. So which might be where Ceres ammonium chloride came from. Yeah.